So, good morning, everybody. Today, I'm going to talk about shape analysis in general and a little bit more specific as well. So it's again a lecture divided in two parts. And well, let's continue. If I get that one running. So first, a long list of literature that you could take a look at. One that is always returning is the one by John Ross. Gives you an overview again. He is usually more like a teaser. So it tells you can do this, but if you want to go into the depth, you need to go into the references he cite. But anyway, it's a good overview giving you some ideas about what you can do. And then of course we can go into more detailed information here. So until now, we have been talking about image enhancement, also image augmentation, segmentation. First of all, by hand, so just trying to find something in the right value to separate the image features. And then we went on to automatic methods and region of interests. Also talked a bit about machine learning, how you can use that for the segmentation and classification. And now we are ready to do something about what we have segmented. So today, we want to know a little bit more about what we see in images. So it could be how big an object is, maybe something about the shape. Is it elongated? Is it more round? Or something like that. Also, do they have different sizes? Some are very tiny, other ones are really big blobs. And maybe we'll also want to compare different images, what the content is. So maybe this image has a little bit more small features, and this one has longer, large features, something like that. But we also want to put the information into a different framework, some kind of modeling. So for example, finite element simulation, or also making pretty renderings. They are usually popular in presentations and in artworks, in publications. They show the user what the sample looked like, maybe not so quantitative, but you get a nice qualitative view and you can have it as a background to discuss around. So first we want to look at the object characterization, then also go into in 2D, and then also talk a bit about the volume case. An important thing is also to know where is the object located, so the center of the object and also its extents, so kind of region of interest for each object, and find a little bit about also anisotropy. We have different metrics that we can talk about. We have shape tensors, principal component analysis, ellipsoid representation, and so on. There is a lot of different metrics we can use. Which one you use depends on your application. So it's really, you probably have to go in the literature to see what the trends are in your specific field. I can give you an overview of common metrics, but otherwise you have to look for yourself a little bit with some critical eye checking. Does this make sense to use? In some cases, one method is completely useless because it doesn't tell anything about your sample, while other ones give really the big highlight about what you are doing. So again, we come back to this slide that you have seen a couple of times. We start out with some imaging experiment, producing a lot of data, and we do some enhancement on it, still get a lot of data, and so it continues. Let's see if I can convince this one to slide. No. And then, of course, you go do segmentation, still have large image, but with less dynamics. But the big reduction in information you get when you start putting labels on objects and reducing them into more abstract descriptions. And that is what we are about to talk about today. So we want to know something about images. We want to know some volume fractions or maybe counting objects, looking at object shapes, or also how the volume is varying among different objects. And to do this, the most important tool we have is component labeling. And with the segmentation, we could get an image that tells those voxels are belonging to a certain category, and those are belonging to some other category, and then the rest is background. But still, all objects of one category, they have the same, they cannot be identified. So we need to do something to identify these objects. And that's where component labeling is coming in. Because what it does is to identify all connected pixels or voxels in an image and give that a label. So if you have a lot of grains, cells or something in the image, each gets an ID number that you can have to start doing analysis on. The component labeling has its drawback, in particular when you have objects that are touching each other, then it can't distinguish that there are two objects, and that's a problem. And for that, there are other methods. Actually, you're going to try one in the exercise. It's called watershed segmentation. It's very useful and popular to identify and label touching objects, which is actually in many natural applications actually the case. So let's look at what we can, our tool for that. That is, first of all, we need some images. We have this scene, I think it's from Aachen, a street, a building, and on the street you can see some cars. And well, you have 1, 2, 3, 4, 5, and possibly 6 back there. And when you do a segmentation, I don't say which type. In this case, I actually only got the labeled image. So I don't even know myself how they did it. But anyway, we have the cars here. In some cases, the cars are cut up, like this one. There was a street lamp in the way, so it's actually putting a line through the car. And this one is, I think there is a tree and a lamp as well. So that one is pretty cut up. But anyway, we have our cars in this segmented image, but we can't tell. We only know that the white ones are cars, but we don't know that the one to the left is car number 1, the one next one is car number 2, etc. So for that is where we need this component labeling. And of course, there are already implemented algorithms in scikit image morphology. There is a function called label. And if we look at the help of that one, you can see there is a lot of functions. It talks about connectivity. And that's something we are going to look into a little bit more in a few minutes. So you can look at one connectivity. So it's only looking along the principal axis of the image, or 2 connectivity. Then you also look at the diagonals. You can also do some other stranger connectivity if you want to. So this is kind of a diagonal connection. And with those, you also decide how well the image is labeled. So let's take a look at one example. We did now run the component labeling. And you can see that the pure black and white image has now turned into several colors. So this actually got some number here. This one got another number, which is now interpreted as color. And then you can see that these actually get several numbers, and particularly this one that is cut up into 3. So let's take a look at how big these objects are. We now start counting how many pixels are placed within each label. And one car has very many pixels. No, actually, I think this one is, must be the background. Yeah, that's the 0. And then the cars, they have different counts. And from that, we can actually tell the area, because in this histogram, each label, if you count the pixels in one label, that's actually the area. So if you multiply that by the pixel area, then you get the area of each object. If you would have a volume image, then it would be the volume of each voxel multiplied by the count would give you the object volume. So it's a very quick way to measure the volume of an object. You don't have to do a lot of fancy geometry calculations, etc. There was a question, I think, or not? No? Yes. There is a question if the label function shows the label for each object, and yes, normally it does. In particular with this component labeling, then it's more like a sequence how they appear. If you do watershed segmentation, you can control which label it starts with, because then you need some kind of seed, and that seed actually gives you the label. But in the component labeling, then it's something automatic assigned. Okay, that is what I told you just now, so good. Let's see, let's continue. So the algorithm, you can do it in different ways, and let's look at an example. We can start with either labeling foreground or background pixels. And let's run this example where we have a very simple image. This is not the most efficient algorithm that I'm going to show you, but it's one way of doing it. And it's very illustrative, that's why I'm showing it. So we start out with the image, which only has 1s and 0s, and we need to do something about that. And let's see, nope, I'm in the wrong place. No. And it doesn't move on. Yeah, there it is. So what we do is now we start giving, say, starting assignment. So each point, so each pixel in the image that is foreground will get a value, and the value is the position of that pixel. And that is the first step as an initialization. And then you can see that the first pixel gets a 1, and down here that one gets a 9. So if you continue counting along the rows, then you get the next one here is 11 and 17, etc., etc. So that is already giving some initial label on these regions. But right now, each pixel is considered to be a region of its own, which is not true because they are connected. And then we can do an iterative approach where we let go through the image a couple of times and checking every pixel that belongs to the neighborhood of a labeled pixel is checked, and its pixel gets the label, the minimum label, except the background, of course, minimum label of its neighborhood. And that's repeated until no more labels are changed. And the implementation of such an algorithm would look something like this. Maybe quite a lot of code right now, but the important things you can check, let's see, is this line here where you get the new value, which is actually checking in the neighborhood. So we have a loop over the X and Y, and then we have inner loops around the neighborhood. And let's run this one, and something happens, and I need to go out to show you what's the outcome. And here you can see that in the first iteration, if you go on this one, its minimum is a 1. When you come to this one, it was, I think it was 11 before. That one has, in the neighborhood, has a 1 in the as a minimum, so it gets the label 1. This one saw before that there was 11 here, and that is what that is getting. And then we go to iteration 2, you can see that the 1s, they are propagating down this object, same way as the 49s are propagating up along this one. And the 9s are going up along this one, and 51s are going down this one. And next iteration, you can see that all are actually labeled already. And then we need to do a last run to check that there is no more changes. And let's go on to the slides again. So we can do a little bit of animation. There are, of course, a lot more efficient algorithms. Some algorithms, they do a forward and a backward sweep of the image, and then they have actually all the labels. Other ones, they do more like this one, a brush fire. So it sees an object, object pixel, and then it's like a brush fire within that object, iterates like a region growing approach. Depending on the image composition, one is more efficient than the other one. So you have to choose more or less which algorithm you use. But let's look at the iterations of this one. What happens. Here you can see how it animates in a different, in a more illustrative way. So it's a little nice movie where you can see what happens. You can also see how many groups you get, and so it continues. So let's go to a little bit bigger images. So how does this algorithm apply to something more than 9 by 9 pixels? Because that is just a little test example. Let's take one of the cars in this labeled car image. So we get this image where we have the binaries, lots of ones, and then we've put the initial labels. So it's actually, again, the pixel index of each point, and it's running through here. And let's see what's come out when we start doing the labeling on this one. Again, with an animation. So let's see, that was the run. And now we can do the animation and see what how it shows. So now you can see how this front is propagating through the image all the time, following the principle that the minimum label within that object is the one that is assigned. If you don't like to have labels like 23 and 38 and want to have something else, like a sequence of labels, then you have to do a remapping after the labeling with this algorithm. Other algorithms, they would be giving the numbered sequence directly. So depending on the algorithm, you need to do a little bit post-processing to get a nice line. But in some cases, it doesn't matter if you have these strange label numbers, as long as you know what they mean. Now we looked at the neighborhood, the full 3x3 neighborhood. And we want to look what happens if you change the neighborhood size. For example, going to 5x5. And the algorithm is a little bit changed. So we need to loop over different neighborhoods. So in this case, it's ±2 in X and Y, like you see here. The test or the value is still assigned the same way. So it's a minimum in the neighborhood. And let's see what we get out of this. So it's run, and I think I need to leave this slide because it doesn't work in the way. So what you can see now, now it's a 5 by 5, and you had less iterations. But what you can see is that when the kernel, which is 5 by 5, it's moving. Actually, if you look at this point, it actually expands all the way over here. So you can see that there is a label leak across this empty opening between the two objects. So that means we will end up with just one object label in this case. Sometimes it's good, but mostly we don't want it. So stay away from larger neighborhoods than just a simple 3 by 3. The other alternative is to go for a smaller neighborhood. So looking at the cross instead. So the first one we had ones all over the kernel, but now we just look into the orthogonal directions. And running this, we get something else. First of all, you can see that there are many more iterations. And now when it propagates, you can see that we actually end up in 3 different objects. Because if you put a cross here, you wouldn't be able to see this corner object. So that one gets its own label. Let's go back to the slides again. So when we now compare the different neighborhoods, you can see that the neighborhood size 3 by 3 solved labeling within 9 iterations. We ended up with 2 segments. If we do the 5 by 5, we finish in 5 iterations, and then we only have 1 single segment out of it. Finally, when we have the cross, we have more iterations and end up with 3 different segments. Iterations, of course, they change with the neighborhood size, but also the complexity of each iteration also increases. So here you do 8 comparisons. Here you do 24 comparisons, and here you do 4 comparisons. And that is also a different thing. That execution time is probably not that different depending on the neighborhood size, because less iterations but more comparisons. So let's see what we can do with them. We have all our labels of the objects. So now we can start counting voxels in each label and get the volume using, for example, a histogram, as I said before. Or we can change it, what happens when we do erosion and dilation, because that will actually change the surface area and volume when you do this. So now what we want to do is, when we have all these objects, we can start counting cells. That's a very easy one. Essentially just count how many labels you have, then you have your number of cells. But we are probably more interested in looking into what is, how is a cell composed, what is the geometry, etc. What is the intensity variations within it. And also we may want to compare different cells within the image. So now is the question where we start. And one thing is looking at the position. So for that we have a center of volume with a single object. We can actually expand this algorithm into having several objects. It's not that difficult. You could do it as an exercise if you would enjoy that. But in principle, we have our image. We change it a little bit, that we have the label. Now we change the image into that it gives a 1 if the label is equal to the one we want to investigate. The algorithm then looks something like, first the black and white labeling. So we had this image with our labels in it. And now we want to look at the ones only. And let's look at that. Let's see, that was the end one. And now we want to define a center. And the center is actually defined as the average of pixel positions in each direction. So for the X position, we have the average of position times the pixel value at that point. Oh, pixel position, no, yeah, pixel position and pixel value. And that for each direction. And let's see what it looks like as a code. We check here, we go through the X and Y's. If label of image is equal to 1, then we start adding up positions. And afterwards, we can compute the average as a position. And let's run this. And we get the coordinates of label 1. It's a pretty long list, as you can see. And the average position that we compute is around here, which actually makes pretty good sense. If I would now change it to look at only the label 2, then I can change it, and then we get the center of the volume in this area. So you can actually pretty easily change it and compute the center of each position. So this would be the label, and you could expand this by having, instead of just single variables or single lists for each coordinate, you could have a list of a list. So you have a list for each label, and in each label you have the positions. And with that, you could then do averaging for all positions. Fortunately, this is such a frequent task that it's already implemented. So you don't have to care about doing this. It would be more as a programming exercise if you like to do it. Oops. No question? Nope. Now, we did it only assuming that it's a homogeneous object, so it's only ones and zeros in the image, but you can actually also expand it into using gray levels, and then you can get a center of mass. So some objects, they have inhomogeneous gray level distribution that actually, if you are looking at transmission imaging, like X-rays, it corresponds actually to a local density or local weight, because you already know the volume of that area. And now if you use the gray levels instead, when you compute this, you can get a different position in the image, and that's actually the center of mass. So let's try with an image which has a gray level gradient, as I show here. And the segmented one would look just like a black and white. And computing the centers on this one, then I need to go out again. Then you can see that the center of volume is perfectly in the middle of this image, while the center of mass has been displaced, because this is a lighter region and this is a heavier region. So it's actually displaced along this line. So it actually makes a difference. And depending on your task, choose the one that you need. In some applications, center of volume is perfectly sufficient. In other cases, you want to know a little bit more about how is the weight distributed within the object, and you need to go for the center of mass. And let's see, there it is. And these were only two. What we can look for is also area. If you do it in 2D, it's counting the pixels. Surface area of a volume, then you have to look at all the pixels that have connection to the background and count those. So that would be a different metric. That would actually be corresponding to the perimeter length in 2D. So it's when you go up one dimension, the whole metric measurement approach changes or shifts a little bit. Sphericity is a ratio between volume and surface area, and that gives you an idea how round an object it is. And the sphere is, let's see, I think the sphere is the largest value you can reach in this context, and everything that is more elongated has smaller values. Orientation is also interesting. Oh, well, for sphere, not really interesting because it's round. You can turn it any way you want. But as soon as it's getting something that is elongated in some way, then the orientation can be interesting. And well, as people usually do this, there is a collective function in Python called region props that gives us all this and a lot more. So looking at the manual for that one, you can see that there is already a lot of information. You can get the area, you can get the bounding box, you can get volume, you can get, yeah, well, you can look at the help yourself and go into the details. Some of these region properties may be useless for you, again, but other ones are just right on what you need. So you have to make a selection among these region properties and select what you want to have. So let's look at what we can get from our image. So looking at this car image again, we can see that the area is 900. The bounding box is 10, 10, 40, 40. We have some box area, which is bounding box area, which is the same in this case. The centroid is located at 24.5, both. And then you can see all these different values, some more or less complex than the others. The Euler number is something that's very important, for example, in porous media applications, that tells how porous an object is, how connected the pores are. So if you have a lot of separated items, like in a gas, things are floating around, or if they are really touching each other, are they completely fused together, or is there some void? Are there channels between? The Euler number tells you a lot about this. So it's a very useful metric within porous media research. Well, some very simple measurement is the extents. So it's essentially the bounding box. It gives us the directions in X, Y, and Z. And how big it is in that way. So it's like you take a caliper and measure in each direction, but you have fixed object, doesn't say anything about the rotation. And in some way it's too abstract and also too specific. So if you have like a banana and you put it in one direction, it doesn't really tell the length of the banana. But to do that, you need a different way of measuring it, but it can give you an idea about the extents. Also look at this case of a cell. Probably not many biologists ask how long is a cell in the X direction, because it doesn't really make sense, because a cell may be not perfectly round and a little bit ellipsoid or something else. So in some cases, it doesn't make sense at all, but it's a very good guiding number to have this, in particular if we want to identify regions containing something. So I look at the car again. We have it like this, and that's a different car, actually. Let's look at it. And then you can see that the extents are in X goes from 4 to 12, and in Y it goes from 3 to 15. And from that, we can do a nice little bounding box around the car. And that's can be good as a visual guide. Also, when you start doing segmentation, identifying objects to put boxes around them is pretty simple. It's also a quick rendering. So if you have many to do, it can be helpful doing it this way. So let's see what we have in the original car scene. Here we start this little example again. There we have the labeled cars, and we want to put some, let's see, I got it wrong. So we do some shape analysis of these cars, and look what we get. First of all, we get all the bounding boxes. We get the center points of each car. So far it works actually for multiple objects. And all this you got using this region props function. So you don't have to implement all this. It comes for free actually. Well, some computation on time, but as you also saw when I executed this, it was in almost instantaneous. Oops. And now we can start getting statistics about these cars, and then it gets a little bit more fun. So you can see here you have label 1, has a bounding box like this. It has an area of a little bit more than 1,000 pixels, and the centroid, then you know its location. An interesting thing here is this color. Based on the average color, you can, with the help of a function called web colors, you can actually give a kind of a rough estimate of which car these different cars have. So mainly it's dim gray, silver, dark slate gray, powder blue. So it's not very exciting cars that are driving around in Aachen at this time. No red and no yellow cars. Well, anyway, so you can get at least an estimate. And if we would go back looking at the image, you can see that, well, it makes sense which colors it's selected. And it's actually using, for getting these car colors, it's actually using a K-neighbors classifier. I have talked a lot about round objects and elongated objects, and a way to describe it is to use the anisotropy. And well, in the dictionary, it defines varying magnitude according to the direction of measurement, which may be a bit abstract and maybe not so precise. But anyway, it's a description that the object changes. There could be different, put it in words, you could say tall and skinny, short and fat, or perfectly round. So that's a way to tell about the shape of the object. Actually, short and fat and tall and skinny is in principle the same thing. So giving this unprecise definition, you can also make different ways of measuring or quantifying these values. You can take the longest side divided by the shortest side, -1, shortest side minus longest minus shortest side divided by longest side. And you can see it goes on like this. It's just a question of your imagination how you combine the metrics in longest and shortest. And it's more or less your choice. Sometimes what makes physically sense, and in other cases, what is used in the community normally, and other ways. So let's look at something here. Looking at the bounding boxes. No, I was just defining a couple of functions. And now we look on to what happens with the anisotropy metric when we run, when we change the shape. So it starts out pretty round, and then we elongate it, and you can see that some of these they fly up in the sky, while other ones, they keep pretty flat. It's more linearly. So depending on what behavior you want, in some cases you want to really punish or praise things that are very thin or round. In other cases, you just want to have some kind of linear metric. So again, what you use is your choice. Let's see, that one should be executed. No. So let's go on to some other tools that we can use. Statistical tools, what we can do with statistics. And in principle, what we're going into now is a combination of two very interesting things from linear algebra and statistics. One is eigenvalue decomposition, and the other one is covariance matrix. And together, they give a very nice tool for us to do a statistical analysis of objects and the distributions of pixels. That is the principal component analysis. We have until now, with k-means, been able to start with vector, trying to identify different regions on objects in an image. But principal component analysis, they're not going on distinct objects, but more on statistical similarities in data. And we are working with a linear combination of different components, and these components, they are actually the eigenvalues of the covariance matrix. And now we try with an example. We simulate spectroscopy, and we create a couple of peaks for two materials, in this case, fat and protein. And then we also have a noise curve. And doing this, we get some values. Right now, they are not so visible, so I have to change now. I think I need to stay in this mode for a little while now. Looking at the protein curve, you can see here the x-axis, the intensity at these points. So we start out in this side. You can just see that it's a lot of noise here to begin with. The noise also just noisy, and then we have the fat spectrum and we have the protein spectrum. So what we want to do now is to test what kind of value we have, what kind of spectrum we have in the data. Is it more fat-like, or is it more protein-like, or is it just some kind of noisy something? So now we want to analyze this in a good way. And the first approach would be just to look at the curves. We have many very noisy curves. It's very hard to tell what each curve actually shows. We could try doing a scatter plot comparing different curves. So curve 1 and 2, they would actually be corresponding to fat and protein. And you can see there's essentially no correlation at all. So it's very hard to do anything with that. Now let's run it through this principal component analysis using 5 components. Run a fit, and it gives us the response that we did this, had a successful fit. And then let's run it. And all of a sudden, when we start looking at the different components, we have curves like this. So these are the transformed components out of this fitting. And if we start plotting component 1 versus component 2 for the correlation score for those, then we can see that we have nice clusterings for 3 different classes. And that makes it much easier to do afterwards. You could do k nearest neighbor on this plot, and you would get a very nice separation between the different classes in the data. So it's a way to wrapping the data around in a different way And with that transform, you have a much clearer view of what we are talking about. So this is one way of using it. Also, when you have noisy data with low information content, you can actually do a data compression using principal component analysis. Most of the information is present in the first few principal components, and the rest is going steep down into almost nothing. An interesting, and we can look at this, for example, we can see here that the first components have a lot of explained variance, while the remaining 3 in the data have almost nothing. So that also helps us to decide which components we should look at in our analysis. An example from the scikit-learn webpage, they do phase analysis. So we have a data set of a lot of phases, 400 normalized phases. So the images are prepared in a way that they are easy to do analysis on. And then we can see the phases first look like this. And if we do principal component analysis, we can see that the first image more or less gives the face shape. The next one, well, the nose gets a bit pronounced. And at some point, also the eyebrows and the glasses come out. On some, the eyes, I would say, probably guess that the beard is also coming out in this one. So each component can have a representation of what it actually shows. It's not easy to do this categorization. You must know your data and even look at the components in these each element in these components, see how they're combined to get a conclusion about what it is. Another thing about it is it's not physical explainable anymore, or possibly with a lot of work. So you can't say that the principal component of this is exactly this physical quantity. That's usually not possible. But it's a good guide and helps. It's actually used in many machine learning approaches to reduce the data and make it more specialized, to point out these are the things I need in order to make a good conclusion about the image content. So let's go back to slide mode again. What we can do about the shape tensor is a very interesting thing. You can, with the help of principal component analysis, where you look at the distribution of X and Y values, you can tell a lot about the shape and also the orientation of an object. So it gives us the optimal rotation of the coordinate system for each object. So you can apply it to each object in your data. And looking at some math, the covariance matrix would be the vectors of X and Y and Z coordinates, and they are multiplied with each other to get this correlation matrix. And if you run the eigenvector decomposition, you would get 2 matrices, one with the eigenvectors and one with the eigenvalues. The eigenvector matrix is essentially a rotation matrix of the coordinate system. And the eigenvalues, they tell you about the length of the vector in that direction. And that's really helpful now that we want to tell something about our images. Like this car, if you run this example, run a principal component analysis around it, and you can see that now we got a rotation of the object, which was like this before. You had this little notch here and a peak here. And it was rotated in a way, maybe not ideal, but now in this way, it's rotated so that we have the longest axis in this direction and the shortest axis in this direction. And you can also print in the component vectors, and you can see here how they are organized. So we can use it to calculate statistical distribution of positions and correlations between them. You can use it as a data reduction tool, and with that we can also estimate magnitudes and sizes of the object. And this is also a tool that's already implemented, so you don't have to go down and do your own covariance matrix computation, and you don't have to do the eigenvalue decomposition. It's already a prepared tool that you can use directly. You can also use it to describe the objects as an elliptical model. So instead of having a bounding box, you could have an ellipse around the object, which is rotated, and the principal components eigenvalues, they tell how this ellipse should be shaped. Last thing, I'm running out of time, I think, before the break. So, but anyway, the last thing is meshing. What we do until now is we have our objects, but sometimes it's difficult to do any further modeling on it. So we need to describe the surface in a more abstract way, and this is using vertices and edges that are span up the surface of the object. And this is very useful, for example, when you want to do finite element analysis, where you want to put forces on different places in the image. And then you can point out, see how the edges, how they stretch, and when the forces are applied. And that's a typical approach in mechanical engineering. So what we need is to look at how the structures are defined by this, how this mesh is built. And in principle, what we need to look at is which pixels are belonging to background and foreground, and only look at the surface pixels and connect how they look like. And there are so many different approaches. Also the surface, if you look at voxel surface, you can see from my previous slides, these different representations of spheres. They're not really sphere-like. And with the help of meshing, you could produce something that looks more like a sphere than these objects here. And a popular algorithm for doing this is the Martian cubes. And it's looking into 2 by 2 by 2 neighborhoods. And a very nice video showing how this works. The first part, at least. The second part is about the coding. If you like that, of course, continue watching. But the first part is very nicely animating how the Martian cube is working. Sometimes cubes are not the thing you need, so it's maybe better to use tetrahedra. And they are actually more precise in describing the objects. In some cases, people are using that, and in other cases, Martian cubes, because it's easier to implement. So that was it for now, before the break. Let's take a short break now, and see you in, would it be fine with 5 minutes? I think so. Then we come along. So I would say 10:15 we continue, and then everything goes on with the advanced segmentation. I have a little question here somewhere. Just have to convince my, oh, there it is. There was a question about the principal component, if they find orientations and directions, why not just use the image moments? That would be a way, but it's not always just about orientations. It could also be about separating different features. So if you have, it's more about when you have multivariate data, then you can use it as a reduction tool. Principal components for finding directions and orientations, sure, you can use the image moments for that. That's true. But it's just showing that you can use it for this purpose too. I don't know which one would be the fastest one. Could be actually that PCA would produce the result quicker, but that I need to check to be sure. So anyway, that's another way of doing it, using the image moments. Yes. So let's have a break.